Hi, my name is Pritesh Rajaguru, and this is Physics 2212, Lab 5, Faraday's Law. So we have two purposes for this lab. One is to collect observational data of a magnet falling through a conductive tube aluminum foil, and the second is to model the magnet and tube interaction computationally and observe Faraday's Law. The fundamental principles we will be using for this lab is Faraday's Law, Ohm's Law, Biot-Savart Law, and Newton's third law. So the procedure of this lab is really straightforward. So first, you record the north and south sides of the bar magnet. Then you record the dimensions of the aluminum pipe. Place the bar magnet north side first into the aluminum pipe so that it doesn't scratch the edges of the inside of the pipe. Next, record the time it takes for the bar magnet to reach the bottom of the aluminum pipe using either a phone or any kind of camera. So repeat this 5 times and average the result just so that there aren't any outliers. So these are the measurements I recorded from my pipe and bar magnet. As you can see to the left you can find the length, width, inner radius, and outer radius of the pipe, and near the bottom you can find the mass and the dipole moment of the bar magnet. So the dipole moment is gotten from lab 3 because that's the lab that we use the bar magnet for. And I conducted 5 trials and averaged the results from those trials, and I got an average time of about 1.24 seconds. So here you can see the initial conditions for my glow script code. So as you can see for step 1 to the left, you can find the different conditions for the pipe, including the length, the width, and the radii. So, and to the right, you can find the mass and then the magnetic dipole moment for the bar magnet as well. Note that the magnetic dipole moment was not the exact same as lab 3, as 2.44 actually caused a skewed graph compared to a proper one. So as you can see here, this is the magnetic field and flux code for my glow script model. At the top is the magnetic field of the dipole, which you can just grab from lab 3 as well. That one's it's just uses the basic formula for magnetic field of a dipole. And at the bottom you can find the magnetic flux of the magnet as well. Note that we are using the general formula, so not the simplified one, as that one gives the most accurate model for the flux. So here are the calculations for my glowscape code. As you can see, it starts off by finding the force of gravity and ends with modeling the bar magnet as well as the pipe. So as you can see for step 4, this is where you find the currents going through each ring, which is then used in step 5 to find the magnetic field of each ring, and at step 6 you find the force on the ring by the bar magnet as well as the force on the bar magnet by the rings. This is then used to find the net force, which is just the force of gravity plus the magnetic field, the force of the magnetic field. And then at step 8, you use the net force to then plot the bar magnet and its velocity. Here you can see my glow strip model. To the left, you can find the aluminum pipe as well as the bar magnet going down it. As you can see, the north face is down while the south face is up. Then to the right, you can find my velocity versus time graph. You can see that the time it took was about 1.372, which is actually longer than what we calculated at 1.24. Here I used the magnetic dipole moment as 4.9 rather than 2.44, as 2.44 actually gave a exponential decay graph rather than a proper graph that looks like this. So time for some discussion questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change then? So the induced current would actually become larger, therefore making the time for the magnet to fall even longer than it was before. What if there were holes or slots cut into the tube? How would this affect the ring currents in your model? So less rings would have an induced current then, which would then cause the magnetic force to become smaller, which would also in turn make the time decrease. Why can't we use a Ferris tube? A Ferris tube would interfere with the magnet as it is magnetic. An aluminum pipe is non-magnetic, so the magnet will not stick to it and it will fall freely through the tube. So I thank you all for watching this and I hope you all have a good day.